Okay, I guess we can start. Are there any specific questions you would like me to go over first? How are we doing? Yeah, sure. Let me see what that one said. Um, okay. Oh yeah, this is a nice one because it just uh combines two substitutions. So, well, I don't know if I made a typo or anything like that. Uh, Question 2 of quiz 10. Let me see. Well, let me write this first. What was question 2 of quiz 10? Uh, well, we did do some problems. Oh, did I not? I mean, yeah, in principle, you should remember that if I give you the velocity, then you can find the position by integrating it. So yeah, that's a good important thing to remember. I mean, I suppose like implicitly, like yeah, besides I mean, this PDF of for practice problems for the final is more like in a sense extra problems. Like you should also check the quiz problems. But yeah, like the only thing you have to remember is that if you're given the position, like if you're given the velocity of a car or a particle, then the position is an integral of that. So it's like an integration problem, but with that extra information. Yeah. So yeah, you should check that out. Okay, so for this problem, first you the idea again, like the way we're computing definite integrals is to do the indefinite integral first. So let's try to find the indefinite antiderivative. You can do that in two steps. So first you can do a simple substitution, which is u equals x squared. If you do that, then the u dx is 2x. So du over 2 is x dx. And so tangent becomes tangent of u. And uh, x dx becomes du over 2. Is that making sense so far? And then how do you find this one? Okay, actually yesterday we did the integral for tangent, if you remember, but I mean, that one may be harder to memorize. So to find the integral from tangent, you just have to use the trick of rewriting it as sine over cosine. So you can write this as 1 of sine of u divided by cosine of u du. And now it's the same idea. You make a substitution. It's just that it is a little bit weird to call the substitution u again because you're already using that letter. So it's just better to use a different letter for that. And so if you do that, that's kind of the same substitution we did yesterday. You end up with 1/2 of sine of u du becomes minus dv. Okay. And cosine of u, sorry, cosine of v, cosine of u becomes b. Okay. So it's minus 1/2 the integral of dv over v. And this is minus 1/2 the natural log of v plus c. So and then what I have to do is start substituting back things, but is this okay up to this point? Uh, what you end up doing is like v was cosine of u, right? So that's the first substitution that I'm putting here. Let me put it in here. But then u was x squared, right? So okay. So the integral, so what I'm saying is that the integral of x tangent of x squared dx is minus 1/2 ln of cosine of x squared plus c. And again, you must remember the philosophy about these integrals, which is that if you're not sure if this is the right answer, you can always take its derivative and see if you get whether you get the stuff on the inside or not. Okay. I mean, in this case, to take the derivative, if you want, like you can ignore the absolute value, just for the purposes of taking the derivative, and you'll see that it gives you the right answer. The absolute value makes not much of a difference in this case for like finding the derivative. So it is that would be the value, but sorry, that would be the antiderivative for the indefinite integral. But then for the actual thing that you care about, which was the definite integral, I think it was being integrated from 0 to root of pi over 4. Let's see, what's the correct values? Yeah. So I'm integrating that from 0 to root of pi over 4. And so it's just take the antiderivative, the value for the expression for the antiderivative, and evaluate it at those values of x. Is that making sense? So let's just plug that in. So when you put x equals root of pi over 4, you get minus 1/2 of ln of cosine of x squared, but x squared is pi over 4 plus c. That's what we get when you put x equals root of pi over 4. And then what do you get when you put x equals 0? So this is what you get when x equals pi over 4. And then what do you get when x equals 0? We get that. This is what you get when x equals 0. Okay, and now we just have to simplify a little bit. So what was the cosine of pi over 4? Cosine of pi over 4 is like root of 2 over 2. You get minus 1L, 1/2 of logarithm of root of 2 over 2. The constants as usual go away, so you don't have to keep writing them. Plus 1/2 natural log. What is cosine of 0? Cosine of 0 is 1. So that's what this is getting you. Is that making sense? It's just a natural log of 1 is 0. So if you want, you can just leave the answer as minus 1/2 ln of root of 2 over 2. Okay, this one, you can simplify. Like I do expect you to know how to simplify this because I am expecting you to remember the natural log of 1 is 0. So that one you should simplify. This one you can leave as it is. Like there are other ways to rewrite this. It's using the properties of natural log, but that's not, I mean, that's not too important because we don't know, we wouldn't know what the natural log of root of 2 is or natural log of 2 is. So it's not too crucial to simplify this further. It could be simplified a little bit or rewritten a little bit, but it's okay to leave it as it is. But this one, yeah, I do, like for ln of 1, I do expect you to use the fact that this is 0. So, is that making sense? Uh, any other questions about this? About this particular problem? I don't know if that's what I wrote on the answer sheet. Hopefully it's correct. But that's kind of like the idea of this problem. I mean, if you memorize the value for the integral of tangent, then you don't have to do a second substitution, right? So only one would have been needed. But if you forget about how to find the integral of tangent, you can find it using something like this. Okay, we can keep going. So anyone else? What other things should we talk about? Okay, what was constraint 3? Oh, this one is a nice one. Yeah, yeah, yeah. Uh, so this is a function of x. So the question asks to find the critical points of this function, right? So anyone remember? So what was a critical point? Critical point is where the derivative was 0, right? So we need to set the first derivative equal to 0. But what's the derivative of this function? Again, this is where the fundamental theorem of sorry about that. this is where the fundamental theorem of calculus is going to get used, because like the fundamental theorem of calculus, what it says is that whenever like a derivative is an integral, right, they kind of cancel one another, and you're just left with the function inside the you're just left with the function inside the integral, but in terms of the variable that appears in the upper bound. So you end up with x squared minus 1 to the 99. Is that making sense? So what I'm saying is that f prime of x is actually x squared minus 1 to the 99. Yeah, is that okay? And then then the question is, when is this zero, right? When does this become zero? Well, this is actually 99 products, like you're multiplying x squared minus 1 99 times with itself, right? So the only way for it to be zero is that if one of these factors becomes zero, right? And that's how you get that x equals plus or minus 1. Another way to think about it is that you can take like that 99th root on both sides of the equation, but that's maybe a little bit more confusing. You just think, well, this is essentially the same expression, but multiplied with itself 99 times. So the only way for all those products to be zero is it at least one of them is zero, but all of them are the same. So that forces x squared to be plus or minus 1. Is that making sense? So in fact, we can do an extra part to this question. So here's an extra part to this question. Which would be to classify these points, right? So are these critical points local? Okay, what would they be? Would they choose? Could I? Okay, this. Oh, right. This like, would this work? Okay. Yeah, for this one, I guess it is a bit tricky. Okay, we can ask, I guess, as an extra question, I could ask, where is this function increasing or decreasing? That's fine. Okay. Let's ask that first. Where is f of x? So remember that to find where a function is increasing or decreasing, you have to do the chart. I mean, you can like use a first derivative for that, right? So this first derivative becomes 0 at 1 and -1. So you should definitely indicate those points in the sign for the first derivative. And okay, let's see if you remember this. So how could you find whether the first derivative was 0 or was positive or negative outside the critical points? Well, take your favorite point here. Like the easiest point to take here is 0, right? And what's the value of the first derivative of 0? Is that, are you getting a positive or negative number? You're getting something negative because you're getting like -1 to the 99. And so if you multiply a negative number an odd number of times, you get something negative. So good, this is negative. So that means that the first derivative, the function is decreasing, right, on this interval. And then what happens here? You can take here like a number like 2, right? What happens if you plug in 2 into this formula? You get 4 minus 1, so you get 3. So what's 3 to the 99? Well, of course, I have no idea. It's a huge number, but I just care that it's positive, right? So this one is that making sense? So this is a positive number. Is that okay? And something similar happens here. Like, for example, if you take -2, since this is being squared, you also get 4 minus 1 again. So this is positive. So this is increasing again. So the function is going from increasing to decreasing, right? So what does it mean? This means that -1 is going to be what? A max. Is that making sense? Do you remember this? So -1 is a relative max. And then the function is going from is decreasing and then increasing. So if you think of the roller coaster, it's doing something like this. And so now this one gives you a relative mean. Is that okay? So it's a cute example. It's a cute problem in the sense of like, there's like like kind of like the important thing here was to realize that you could connect the fundamental theorem of calculus to other problems we got done before, because it was just like the odd thing about this problem maybe was that like the function was given in this weird way, but that shouldn't be like a reason to feel intimidated, because the formula for the derivative of a function like this is super easy if you use the fundamental theorem. You just like plug the variable inside the expression. Okay, so it's kind of like more to remind you that you know finding derivatives of if your function is defined in terms of an integral, finding the derivative is actually not too bad. Okay. In fact, I mean, more of an aside, like a philosophical remark. I mean, this may look a little bit weird, so it's more like for intellectual curiosity. But one of the ways, if you were interested in defining things, like if you thought about how the mathematics, like certain functions are defined, but actually one of the ways to define natural log of x, like a way to define. So if you didn't know, if you had never seen natural log before in your life, one way in which it can be defined is using this formula, using a definite integral. And from there, if you took that as a definition, right, it would become automatic that the derivative of natural log of x, right, uh, is 1 over x. This would become like immediate. You would get this almost for free. Um, because it's just a fundamental theorem of calculus. So, like, the advantage of doing this, using this definition for natural log, is that, like, at least a property of the derivative is like completely clear. But then, of course, what's less clear, and also it would be super clear that ln of 1 is 0, right? Because it's like integral from 1 to 1 of the t over t. And like, remember, no matter what you put inside here, if it's going from the same number to itself, you always get 0. So this would also be super easy. What would be more complicated here, what is a little bit more complicated here is to check like the other properties that you typically know of natural log. The natural log of a product is the sum of the natural logs and things like that. That can still be proven using this definition, but it's more complicated. But I'm just saying, sort of it's kind of turning things upside down, where you can take the derivative, like it's kind of, in many ways, that's kind of like the more mature way to do things, where you actually take the definition, like the definition in terms of an integral, but then you just have to verify that it has like the properties you would like it, that you know and love from natural log. But that's possible to do. So I'm just saying that. So this approach is less of defining like a function in terms of an integral is actually less artificial than what it may look like at the in the beginning. Okay. Is that making sense? So I mean, again, it's not something to worry about. I'm just saying that there are ways to use these integrals to define functions that you already know of. Another one that, I mean, just to keep going like this, right. Yeah, I mean, like you can kind of also do something similar for the exponential, but that one is maybe a little bit more weird, more difficult to explain. But I'm just saying, like, you can use calculus in a sense to define like the functions that you studied in pre-calculus, which may sound a bit odd. Um, are there any other problems we should go? You will let me to go over first. Let's continue. Let's see if I can think about an interesting problem. Okay. Um, let's do an implicit differentiation problem because we haven't done those in a while, so that could be fun. Okay, let me see. Yeah, let me do one of implicit differentiation. Uh, well, I mean, I guess everyone has access to the online version of the book. So this is on the book, on the exercises of the book. This is number 42 on section 3.7. Okay, so let's try to find the equation of the tangent line. Okay, let's try to see. I'm not sure if I would be able to plot that on the algebra. Kind of a complicated expression. So let me just check if I would be able to do so. Oh, that's cute. Yeah. Okay, I'll show you how it looks in a second. But let's just okay, yeah, this one could, I see you could. Let's see if let's see if I could also plot this one. Oh, this one is more interesting. So this is a small variation. Okay, but it's based on, so small variation. So I'm going to change it a little bit. I'm going to put a Y here as well. Okay. Let me see if this is going to be fine. Okay, but I don't like this number. Let me see now if I can fix this. Okay, I'm going to change this a little bit. I'm going to make y equals pi over 4. Okay, yeah, this is better. And then, yeah, this will be nicer. Okay, yeah, no, this will be better. This is going to be a better problem. Okay, so let's try to work it out. So anyone remembers these implicit differentiation problems? So the idea was to take the derivative first with respect to x on both sides of the equation, right? And, does that ring a bell? And then, okay, so what should we do now? I need to take the derivative with respect to x of each of these terms, right? But each of these terms is going to require the product rule, right? So it gives you 2x. Remember, the product rule is the derivative of the first factor times the second factor, right? Plus the first factor times the derivative of the second factor. So let me write it this way, and then we can finish it. And then the other one is minus the derivative of y with respect to x times sine of y minus y times the derivative of sine of y with respect to x equals 0. Is that okay? Is that making sense? So far, so good. Okay. Now comes the part. Now comes the more tricky part of implicit differentiation. So it was 2x cosine of y plus x squared. What's the derivative with respect to x of cosine of y? Anyone remembers? What was this? Let me bring more copy while you think about that. Just like in a second. Almost there. You're forgetting something. Be right back. Yes, now that's correct. Is that making sense? Because it was a chain rule, because y is a function of x. That's the whole point of the implicit differentiation, that y is a function of x. So, oh, let me change my speaker. So y is a function of x. So you have to apply the chain rule when computing this derivative. Is that okay? This is what you cannot forget, because otherwise like, the entire problem changes the answer. And now it's something similar here. like it's almost the same idea. What's the derivative of sine of y? With respect to x is cosine of y times dy dx. Equals 0. Are we okay with this? Is that so far so good? Okay, so let's just after you took the derivatives, which we just did, then you can just plug in the values that you were given. So plug in okay. So what do you get? You get 2x, but 2x becomes 2 root of pi over 4. What's cosine of pi over 4? Cosine of pi over 4, remember, is root of 2 over 2. Then you get x squared. But what's x squared is pi over 4. And then minus sine of pi over 4. That's minus root of 2 over 2 times dy dx. Minus dy dx. What is sine of pi over 4 is root of 2 over 2. Minus y, but y is pi over 4. And cosine of y is root of 2 over 2 because it's cosine of pi over 4 times dy dx equals 0. Is that making sense how I made the plugin? So here again, I'm just using, let me write what I'm using. I'm just using that cosine of pi over 4 is equals to sine of pi over 4. So that's, once you remember that, then all of this kind of is easy to follow. So let me simplify this a little bit because it looks a little bit messy. So the 2's cancel here, right? So you get, and if you want, you can move this root of 2 inside this square root. And so you get root of pi over 2. And then let's see, this one, this 2 combined to minus root of 2 pi over 8 dy dx. And then minus root of 2 over 2 dy dx. And then these ones also combine into minus root of 2 pi over 8 dy dx. Is that making sense? In fact, I take back a little bit of what I was doing because here it's better to cancel the 2's, but leave the root of 2 outside. Why? Because then everything has a root of 2 in common, right? There's a root of 2 everywhere, so you can just divide by it. Oh, that looks a lot nicer. So you get minus pi over 8 dy dx minus 1/2 dy dx. Oh yeah, it looks way better. Minus pi over 8 dy dx equals 0. Okay, and then these, I mean, if you want, you can combine these two first. Minus 1/2 dy dx equals 0. And then now you can solve, the idea is to solve for the dy dx. So root of pi over 4 equals pi over 4 dy dx plus 1/2 dy dx. I mean, there's not too much that you can simplify here. You should just factor out dy dx, so put pi over 4 plus 1/2. And the slope would be root of pi over 4. I mean, I wouldn't expect you to simplify this further after you found the value. And the equation of the tangent line is easy because it's just y minus the y value that you were given. The y value you were given was pi over 4 equals the slope, right? The slope is this mess that you see here. So it's root of pi over 4 over pi over 4 plus 1/2 times x minus the x value. The x value was root of pi over 4. Yeah, so it looks a little bit bad. I mean, obviously I would choose more pleasing numbers. It's just like I'm kind of did it on the go. But it's yeah, so it's a little like, of course, like these numbers are a bit too, they're not too pleasing aesthetically, but I mean, I wouldn't expect you to simplify this. But yeah, I mean, I would choose better numbers on the exam where there's a little bit more simplifications. I don't do the test time. But like the idea is to just like you know, do some sort of like cancellation of that sort. I mean, the important thing about the implicit differentiation problems is that you get dy dx. Don't forget to put dy dx when you're taking the derivatives of the things that depend on y. That's what can ruin those problems. Is that making sense? Let's reflection. Okay, let's see. Let me see what else can I find. Okay, I just did one on implicit differentiation. Well, let's do one on logarithmic differentiation, which was the other type of differentiation we talked about before. So let's do logarithmic differentiation as a reminder. Let me see if I find a nice one on the Fluke. This one looks interesting. But that's a little bit messy. Uh, okay, let's do okay, this is going to be, okay, let's do, this is 96 on 3.8. So it's to use logarithmic differentiation. Derivative of So, what was the method of logarithmic differentiation? It was literally taking natural log on both sides before you take the derivative, right? So you take ln on both sides. So you get ln of y equals ln of, this is what is a little, looks a little bit messy. Okay. And then before taking the derivative, you simplify this expression a little bit. So this ln, yeah, so the thing is like, this is kind of like I mean, I don't know, I don't think okay. I guess I don't need, like, I'm debating whether I need that many parentheses in this expression. Let me just put this ln in a different color. Yeah, now it looks a lot better. The thing is that this is just some number raised to an exponent, right? So the properties of ln, the natural log allows you to take the exponent down. So this exponent, you can move it to the front, so you get ln of x times ln of x. Is that making sense? And after that, everything else is more is not as confusing. But this thing about this notation for the ln could have been a bit weird. And so now again, it's like an implicit differentiation problem. So you take the derivative on both sides with respect to x. Okay. Now in logarithmic differentiation, there is a formula for this every single time. What is that formula? This is something you could memorize if you want. What would this give you when you do the logarithmic differentiation here? What is the derivative? Okay, this is an implicit differentiation problem. So what's the derivative of this with respect to x? Yeah, it's y prime over y. That's something, I mean, you can write it one of, we can write it 1 over y times dy dx. Yeah, this is something you must remember. Yeah, so it's always 1 over y times dy dx. And how do you deal with the other one? It's like the product rule, right? So it's the derivative of the first one times the second one plus the first one times the derivative of the second one. Is that making sense? So again, like, because it's being multiplied, so now this is just 1 over x. So it's 1 over x times ln of x. That one is not too bad. But then comes the next one, which is complicated. A little bit more complicated. What is this derivative? So it is a chain rule problem, right? It is confusing. Call this u, right? So it's like the derivative of ln of u is like 1 over u. So you get 1 over ln of x times the derivative of u with respect to x, which is just 1 over x. Is that making sense? So this is a chain rule problem. Is that okay? Exactly. Yes. 1 over x log ln. Yes. And now, I mean, at least these two do cancel. So you can rewrite if we're almost ready to go because this is y times 1 over x ln of x plus 1 over x. Okay, this looks not as bad as before. And yeah, we are almost done. You just have to replace y with its original formula, which was ln of x to the ln of x, 1 over x. And that was a formula. Is that making sense? Any questions about this one? Okay, let's do another implicit differentiation problem to see, because again, this is kind of like a useful technique. So here's another implicit differentiation. So use implicit differentiation. Here's another example. Uh, okay, let's see this. So what was the arctan? Arctangent was the inverse of tangent, right? So if arctangent is the inverse of tangent, what you can do is take tangent on both sides of the equation. And so, okay, good. What happened? What happens with when tangents is arctangent? What does it mean for them to be inverse? What's the property of the inverses? What do you get? What do you get here? What does this simplify to? Yeah, it just simplifies to x. Remember that that's the point of a function and its inverse. Then when they see each other, they kind of disintegrate. So you disintegrate them. So you just get x. So now this is exactly the same setup as before to take the implicit differentiation of both sides. So you can take the derivative of both sides with respect to x. Okay, and what was what is tangent of y? What's the derivative for tangent of y? Sorry, that's what I meant. What was the derivative of tangent? The derivative of tangent is secant squared. So you get secant squared. Am I missing something? What else should I put here? Times the y dx, good. That's what's the derivative of the x of x with respect to x is just one, right? So that gives you that the derivative of the y dx is the 1 over secant square of y. So the derivative of the y dx equals what is 1 over secant? That's cosine. So it gives you cosine square of y. Okay. Is that making sense up to this point? Is that okay? So far, so good. But now what else do we know? We know, I mean, this is kind of the answer, but you cannot leave it in terms of y. We want to leave it in terms of x. So what else do we know? We know that the tangent of y equals x, right? So we want this answer in terms of x. Okay. So here's something you could do. Okay. We know the tangent of y equals x, right? We saw that before. So you can make what was like the definition of tangent in terms of a right triangle? Think of y as an angle. Think of y as an angle here. So what's the definition of the tangent in terms of a right triangle? The definition of tangent was the opposite side to the angle divided by the adjacent side. So if you think of this as x over 1, you can think of this as being x divided by 1. So the tangent of y in this picture is x over 1, which is just x. Is that making sense? But then, what's the hypotenuse for this right triangle? What would be the hypotenuse here? According to Pythagoras' theorem. Well, remember the Pythagoras theorem says that the length of the hypotenuse is just the square root of the sum of the squares of the sides. So you get that. And from there, you can see that the cosine of y, this forces cosine of y to be 1 over root of 1 plus x squared, right? Because y is adjacent divided by hypotenuse. And so the y dx is just the square of that. So that's how you end up with the formula that the derivative of arc tangent is 1 over 1 plus x squared. Is that making sense? So again, it's another implicit differentiation problem, but you have to remember the oh, okay, good. Okay. So you're saying, oh, like you mean in this step from secant to cosine? It's just that secant, like it's also important. It's useful to remember this that secant of y is 1 over cosine. So I mean, you should remember the trick with the triangle. Yes, it's important to know how to find out these derivatives of. It may or may not be on the exam, but yeah, it is useful to remember this. Like, let me see what's another way you can think about this. Oh, just to finish answering this question, like if you didn't want to do the triangle, there's another way to do this without the triangle business. Let me see if I can just explain it in a different way. Oh yeah. There's another way to do it without a triangle. I'm about to do it. So secant of y is, which is more algebraic. So secant of y is 1 over cosine of y, and so 1 over secant is what is cosine. Just to answer the question that someone asked me, to that, like how I got from here to here. That's why 1 over secant is cosine squared. If that's okay. But yeah, let me do this in a different way, which may be easier to understand, which doesn't require this triangle. Because that could be the confusing part. So you had the dy dx, right? Is 1 over secant square of y. But here, I mean, at some point you do have to remember an identity. So there was this identity that what is, so here's another way. What is cosine square of y plus sine square of y? What was that equal to? It's just 1. Okay. And then if you divide both sides by cosine, which we have done a couple of, should I divide? Yeah, if you divide both sides by cosine, I think we have done this a couple times already, right? I think we did this yesterday. You get this. So you get cosine square over cosine square gives you 1, right? You get 1 here. And then sine square over cosine square, you get tangent square, right? And so you end up with 1 plus tangent square equals secant square of y. So of course you can remember this formula, but I don't know if you want to. I mean, I think everyone should remember this identity. I don't know. I mean, of course, everyone is free to remember this one, but it's kind of useful to check how you got it from. Is that making sense? So far so good. But then so that means that the y dx is another way to write this is as 1 plus tangent square of y, right? But what was tangent of what? What was tangent of y? Tangent of y was x, right? So that's how you end up with is that this is 1 over 1 plus x squared. Because since x is tangent of y. Is that making sense? I don't know. Maybe this is easier. This is easier. I'm not sure. And because that way you don't need to remember any triangle, the triangle stuff. But you do have to remember that. I mean, like again, there's not with trick stuff. if there are sines and cosines squared or something, if there are trigonometric expressions that appear on the square, kind of this identity can be useful at times because we needed to get to this one. So that it is, I don't know if that's better, but it is at least less it's more algebraic, for lack of a better word. So if you just had remembered this identity, then yeah, like that finding this is more like mechanical. So you can do that like that. Is that okay? Uh okay, let's take a 5 minute break. That way it should give you time to think about whether you want to ask me something else about the exam. If not, I can try to come up with some other problems. But yeah, I'll give you some time to just pause for a second and think if there's something else that you want to ask about. So let's just yeah, let's meet in 5 minutes. Okay, that sounds good. Sorry about that. Thanks for whoever saw that told me you and with me. So yeah. So I was just saying that yeah, we could do unless there was someone else, some other specific problem you want me to go over, we could do a related rate question because that could be just I think we haven't done for the for the reviews. So just as a reminder of how this work. Um, so third base. Good. So let's see. So it says it's a baseball diamond. Each side is the field is a square. So it's a square where each side is sorry. So the baseball field is a square. Of 90 feet. Where each side is 90 feet. Okay, and then you have a player here. Here it is. So you have a player who's running from first base to second base. So this is a player running from first base to second base at a rate of 16 feet per second. Okay, so that's what you see in the diagram. And the question is, what rate is the okay, so there are two parts to this question, so which I want to answer. So at what rate is the player's distance from third rate from third base, sorry, from third base changing when the player is 30 feet from the first base. And there, okay, so oops, let me give you a second to copy this. So there are these two angles that you see in the picture, theta 1 and theta 2. So this is also asking how fast are these angles changing? I mean, it's the same question. How fast are theta 1 changing? How fast are theta 1, theta 2 changing at this moment? Well, let me put it. Okay, so I don't know if everyone can, I'm trying to show you the picture together with the statement. So let me give you a second to copy this because it is it's a tricky it's a long statement. So I just want to make sure everyone has time to copy it. So let me know before I discuss it. This is like a problem where like finding the correct variables to label is almost like 50% of the problem. Okay, it is very important to find the right variables in this problem. Okay. And it is the diagram itself can make it a little bit more confusing, but as opposed to whether it had been like done in a different way. Like, if he cannot be with respect to second base. But in this problem, it's with respect to second base and the baseball field, so we have to adjust like the diagram to that situation. But yeah, so let's see. What are some options that you could do here? Uh, what are some variables you could introduce? Let me draw the diagram again with less terminology. So we have this square, right? We have this square. You have the player here. Okay. So this problem is asking for, what's the first thing this problem is asking for? It's asking for the distance between the third base and the player, right? So there should be a variable that keeps track of that, right? We should have a variable that keeps track of the distance between the third base and the player. And in this case, we can call that distance like, let me call it H. You'll see why in a second, because if you look at this diagram, they mentioned like, they kind of gave like, draw like a right angle there. So it's kind of, that suggests that you will use like Pythagoras theorem at some point. So it's useful to call this H. So H is going to be the distance between the player and third base. Is that making sense? So part A is asking for the HDT. Is that okay? Because it's asking for how much this distance is changing as you're moving. So far, so good. Are there any questions about this? Okay, so now we need an equation that kind of we need an equation for that's convenient for H. So what else could you do in this picture? What other variables could we have in this picture? What else could you do? Well, remember, each side of the square is 90 feet long. So here's like a side that's equal to 90 feet. Uh, okay, and then this, like, we could call X, right? The distance from the player to second base. Okay, so X is the distance. Is that making sense? So in this diagram, how are X and H related? What's the relationship between H and X? H squared is x squared plus 90 squared, right? That's just Pythagoras theorem. Is that making sense? So that's what Pythagoras theorem is saying. And then, good. I mean, you could find what H, like, you can write this again like this. So, I mean, this is 100, I guess. That's not too important because you're about to take the derivative with respect to t, so on both sides. So what's the derivative with respect to t of h squared? What's this equal to? It's just 2h dh dt, okay? That's like an implicit differentiation. Like, well, it's a sorry, I should have said chain rule problem. So it's just like a chain rule problem. And this one is 2x dx dt for the same reasons. And this one is 0 because it's a constant. Good. So you get that h dh dt equals x dx dt. Okay, so that gives you a formula for the h dt. So what is the h dt? The h dt is x over h times the x dt. Okay, but what is the x dt? That is given in the problem. What is the x dt? Because x was the distance between the player and the second base. So the x dt is the speed of the player towards second base, right? But it is 16 feet per second, but you have to be a little bit more careful about that. Is it just 16 feet per second or is it something else? Should you just put 16 feet per second or should you just, because what is happening, the player is getting closer and closer to second base, right? So the distance between the player and second base is decreasing, right? So the distance is decreasing, right? So what does that mean if the distance is decreasing? A function that's decreasing must have like negative derivatives. So it's minus 16 feet per second. Is that making sense? And then, so this is why this has a minus. So you have to be careful about that because like minus since distance is decreasing. And the problem is asking you to find this when you're 30 feet from first base, right? So here was second base. This was first base. So if there's 30 feet here, right? If there's 30 feet here, that means that x has to be 60 feet, right? Because the square is equal to 90 feet. So it's actually asking you to plug this in when x equals 60 feet. So dh dt becomes 60 feet divided by h over minus 16 feet per second. And so now we just have to find what h is, but h can be found from Pythagoras theorem because h, remember, is the square root of 30 of x squared plus 8100. So that's the square root of what is x is 60 feet squared Okay, well, I suppose in this case, 3600 plus 8100, you can take out, you can write it like this. And okay, what is, in fact, oh, you can even pull out a 9. So h is 30 times square root of 13 feet. So the HDT is 60 feet over 30 root of 13 feet times minus 16 feet per second. And I guess you could simplify this a little bit because this just gives you 2. Oh, that's good. So you get the HDT equals minus 32 over root of 13 feet per second. Okay, so that's the how much the distance is changing at that when you are 30 feet from first base. Is that making sense? Okay, and then the second question was just about the angles, how fast these angles are changing. So let's go back to the diagram. I can put let me copy paste the diagram again. Okay. Oops. I don't know what happened here. Sorry about that. Okay. So in this diagram, this was called, I believe, theta 1 and theta 2. Okay. So for example, what can you say about theta 1? Um, okay, it's kind of the same. Oh, it's better to work with tangent actually. So tangent of theta 1, again, is opposite, the opposite side divided by the adjacent side. So it's 90 over x, or 90 times x to the negative 1. Okay, so again, you can take the derivative with respect to both sides with respect to t. So the derivative with respect to t of tangent of theta 1 is the derivative with respect to t of 90 times x to the negative 1. So you get, what's the derivative of tangent? Is secant squared of theta 1 times the theta 1 dt. And this gives you minus, what's this derivative? Minus 90 x to the negative 2 of dx dt. Okay. And we're almost there. We already had, we already knew that this was minus 16 feet per second. We already knew x was, this becomes 60 to the negative 2. That's good. So it's only finding out, we only need to find the value for secant of theta 1. So how can we find that? Let's do just the right triangle. That may be easier. So we have the right triangle, where here's theta 1. X is 60. We just said that. And this is 90 always. So secant is 1 over cosine. So really what you need is cosine of theta 1. And we had said that the hypotenuse was 30 root of 13 in this case. So the cosine of theta 1 is adjacent, which is 60 feet over hypotenuse. Well, that gives you 2 over root of 13, whatever that is. Okay. So the cosine squared of theta 1 is 4 over 13. And the secant squared is just a reciprocal, so it's 13 over 4. So you end up with 13 over 4 d theta 1 dt equals minus 90 over 60 squared, which is 3600 times minus 16 feet per second. I mean, knowing the units cancel out. I mean, of course, like, I just chose this book out of randomly. I mean, I just chose this problem randomly from the book. In practice, I would never give you numbers which are so big. So I'm not. I don't think. I mean, you could simplify this a little bit if you wanted to, but I'm just saying, like, not kind of like the purpose, like right now. But you could say something like this. This is minus. Yeah, the minus cancel out. And this would be one of the 10 times. It's going to be something like that, I think. Yeah. Because here this 4 cancels, so it gives you 900, and 90 over 900 is equal to 10. You get something like this. But again, it's not, I mean, such simplifications is not the most important point here. It's more like how to set up things. And yeah, I would give you numbers in any case, which are better. And the other one is kind of similar, but there's another trick to find the other problem. So how can you find the theta to the t? Well, actually, you can use a trick. So let me, before finishing today, let me give you a trick. There's something that you always know about theta 1 and theta 2, because here's where you have theta 2, right? What can you say about theta 1 and what is, we know that what is theta 1 plus theta 2 equal to always? Just to go to the picture again. What is theta 2 plus theta 1 equal to? These are angles inside a triangle, right? What are the sum of the angles of a triangle? 90 degrees, right? I mean, this already is 90 degrees. That is never changing. That's always right triangle. So these two together must add up to 90 to make up a triangle equal to 90 degrees. So this is always equal to pi over 2 or 90 degrees. So you take a derivative with respect to time of this equation. You're taking a derivative like this. So this gives you d theta 1 dt plus d theta 2 dt equals 0. And so that immediately tells you that the derivative of d theta 2 is just minus the derivative of d theta 1. So it's a nice trick to have. I mean, otherwise you would need to go over like all this process one more time, which it would be crazy to do. So the trick was just to realize that theta 1 plus theta 2 add up to 9. Okay. So yeah, Isaac, again, for like these related rate optimization problems, like again, the key idea in the word problems is to find like the equation that relates the variables. Like usually the equations that I'm expecting you to remember are like Pythagoras theorem. That's an equation that's useful to have, very useful, in fact. Pythagoras theorem and like the area of like I guess like the area of a rectangle. That's also another important equation. That's just base times base times height. or the area of a triangle, which is just one half of base times height. And then yeah, like these formulas for tangent, what's tangent, sine, and cosine, like in terms of how to find tangent, sine, and cosine from a right triangle. That's also useful to have for these related grades problems. Okay, but yeah, no, yeah, I guess I thought it just made sense to go over this again. So again, this depending on how much time you have for tomorrow's exam to practice, just check the problems on the quizzes, check the practice problems for the midterms and the final and the exam problems. And then if you have time, like you should just, I mean, if you have time to go over our PDFs of notes, that would also be probably useful. But yeah, like the exam, I don't think it's not too crazy. I mean, I think it's very reasonable if you like have been doing the practice problems and things like that. I don't think there's anything too tricky. So I think you'll do well if you have done the practices. But yeah, if there's any issues, while you're taking the exam with your computer or something crashes, like this, I will be checking the email. So like, I think that I think you would do better than third exam if that's what you're asking me. Yes. Well, like, let me, like, in principle, like, okay, what I can do is kind of check how much you have done already. Like, I wouldn't say, I don't think it makes a lot of sense for you to keep doing the homework after tomorrow because tomorrow is the final. So what I will just check is your percentage that you have completed. If you have already completed like 80% or 75% of the homework, I'll just give you all the points. So I will tell you not to even worry about it. So yeah, if there's someone who still needs to complete more, then yeah, I would probably give that person like an extension to keep working on it. But yeah, I mean, it makes no sense for you to work on the homework after the exam. So if you already got to like 80 or 75% of the homework, then that's fine. And yeah, I'm still I'll obviously get the. I mean, this week I'll have everything graded, but yeah, don't worry too much about it. Yeah, that's what I would say. If you already did that much. So yeah, if you have time and you still want to work on homework problems before tomorrow's final, then just do that. But after tomorrow's final, don't keep doing that. Okay. But yeah, so I will again. If something comes up, I'll still be checking my email tomorrow and before that. Okay. Oh no, good. Like hopefully you learn something. So good luck if you take calculus 2. I hope if you continue taking calc 2 or like your math courses. If not, enjoy the rest of the summer. But yeah, I mean, I'll still be around. I mean, again, I'll be checking my laptop tomorrow, my email and stuff like that tomorrow in case like you have an emergency. And also if they're like last minute questions or something like that, feel free to email me. I'll try to get to them before the exam. But I mean, you will be fine if you have been doing the practice problem. So I'm not too worried. I think you will do good. So I'll send you the video in a couple of minutes for today. So with the notes.